On today's Emerging Tech Horizons, power beaming. I see the light, and in the light, there is power. Hello, and welcome to the Emerging Tech Horizons podcast. I'm Arun Serafin, Executive Director of NDIA's Emerging Technologies Institute. Today, we're going to be talking about power beaming technology. Energy, everyone knows, is the fundamental currency on the battlefield. And power beaming is a revolutionary technology poised to transform military operations because it makes that currency much more easy to distribute. Imagine a future where drones, vehicles, even soldiers' equipment can be charged remotely, where near instantaneous energy transports enables military operations. Power beaming, through the use of directed energy like lasers, offers this capability. My guest today to help us understand all of that and the promise of the technical area is Tom Nugent. Thanks for joining us, Tom.
My pleasure.
Tom is the CTO and co-founder of PowerLight Technologies, an NDIA member company. Previously, he was a project scientist at Intellectual Venture Labs, where he was involved in one project I found really interesting, the Photonic Fence project that used lasers to kill mosquitoes. I'd love to hear a little bit about that. Tom holds a Bachelor of Science in Physics from the University of Illinois, and most importantly, a Master of Science in Material Science and Engineering from the Massachusetts Institute of Technology. There's no finer place to get a materials degree than MIT. So Tom, thanks for joining us today on the podcast.
No, it's my pleasure. Thank you for inviting me.
So let's dive into this interesting technology. For those who don't know, can you explain basically what power beaming is and why it's relevant and important to defense?
Yeah, so as you said, energy is critical for anything we do, and it is a core part of what we're calling digital infrastructure. Everything around communications, data transfer, but also sensors of all different types. And power beaming takes electricity from somewhere where it's easy to get or plentiful. It could be a wall outlet, it could be a generator, a solar farm, and then it takes that energy and converts it into light with lasers. And then we take that light and we can send it either wirelessly through the air, what we sometimes call free space power, or through optical fiber cables. And people don't necessarily realize, but you can put amazing amounts of optical power into optical fibers of very, very tiny sizes. Then at the other side, we have specialized solar cells, photovoltaic cells, that are matched to the monochromatic, single wavelength laser light to most efficiently convert that light back into electricity. That electricity we then sort of regulate and then can charge batteries and power devices. And wrapped around all of this is a safety system that makes sure when people hear the word laser, they think, oh my gosh, it's a death ray. And there's a lot of things different about what we do in terms of the beam. It's not like the little tiny pencil beam you see and stuff, it's bigger, but we have these safety systems that act like the insulator on your electrical wiring. It keeps you from getting into the hazardous area unless you turn off the laser before anything can get exposed. So that's the basic.
And so, when we think about the ability to beam power like that, when I try to think about why this is going to provide a tactical advantage to the military, it's a little bit obvious, but what are some of the examples?
Yeah, so drones are one where there are a lot of situations where you don't want them to land, to take time, because you'll lose, say, the eyes on a target, or you'll lose your communications relay for that time. And in some situations, it can be hazardous to someone to go out, retrieve that drone, and change the batteries. Taking a slightly higher level view, there's also the question of, do you want your warfighters to be changing batteries or doing something that's ultimately higher value? Some of the situations are if a group were to roll into a new location and they want to do things like setting up perimeter sensors. If it's a base that might be there for a couple of years, they might trench cables. Well, you've got all that heavy copper you have to bring with. You have all the time and effort of people sort of laying those cables out there. And so that's A, slow, and B, if you've buried the cables, you're probably not digging it back up when you leave in a year, and so it's very expensive compared to power lines that go to your house that might be there for half a century. So there's those time factors. With power beaming, you can land somewhere. However you get the sensors out there, that's about as long as it'll take you to start powering them as well. And it gives you flexibility because the power beam transmitter can always sort of change where it's pointing. And now, if you want to move those perimeter sensors, for example, to get whatever different configurations, you can do that, and you don't have to worry about trying to move the wire. You don't have to send someone out regularly to, say, put fuel in a generator.
And so, I mean, basically, the free space version of this is not shooting it through a wire or fiber,
right?
But pointing something at a device and powering it remotely.
Yeah.
It reminds me of the solar powered calculators, right, that I used to have in school. I guess is it basically the equivalent for people to understand of using solar power to charge up devices, but in this case, instead you're using some kind of a laser?
That's exactly right. And the important differences are that the laser doesn't have to go off at night, and for many reasons, we can be much more intense than sunlight and more efficient. And so, whereas for sunlight, the amount of sunlight that gets to the surface of the Earth, if you're near the equator and at noon, is about 1 kilowatt per square meter of light. And then whatever efficiency you have, you might get a few hundred watts of power per square meter, which is a few hundred watts. That's maybe a couple laptops in a square meter. The power beaming, we can be hundreds of times that intensity. We can have 5,000, 10,000 kilowatts of electric output per square meter. And so unlike solar cells, where just sunlight is very diffuse and you don't get much power out, in power beaming, you can get a lot of power out of a relatively small area.
There sounds like there's a lot of promise here for the Department of Defense, even for commercial applications. What is the technological maturity at this point? What should I be expecting to see rolled out either commercially or in defense in the next 5 to 10 years?
Right. So some of the proof concept prototype demonstrations that we've done have gotten to the TRL 5 to maybe 6 level.
Which means?
It means that they have been not really ruggedized and may not be configured or have all the final sort of weight or form factor of a fielded product, but they've been demonstrated, say, outdoors. We've done testing in light rain. We've done some demonstrations out in the Mojave at ridiculous temperatures. And so we are working and expecting to do a program for some drones, and we're hoping to have that out for a handful of units for some field testing and evaluation in less than 2 years. And fingers crossed, if everything goes well, having that then become a product that can be deployed in larger quantity, a year or two after that.
So when you think about that, the powering of drones, what does this, if I came out to see one of these tests, what would I look at? What does the systems look like?
Right. So the transmitter, I'll say, often they're very boring because it's invisible light. Mm-hmm. And if we have special cameras to see it, you see a spot of light. It's like a flashlight.
Right.
But the transmitter is a box. It's going to have the laser and chiller and controls and everything. And then there'll be what's called a beam director. And if you've seen some of the directed energy laser weapons, it'll look vaguely something like that. So that you'll see a window basically that can move around and point. And the receiver will generally look like some, depends on the size, but it'll be a sort of like a box or a panel that's got a little bit of depth to it, but it's sort of wider and it's got a window over it, and you'll maybe see some shiny bits, something that looks maybe like solar cells inside.
And that's stuck on, retrofitted to the drone or built in intrinsically to the drone.
Yeah.
And range is up to as far as you can shoot the laser.
Yeah. So
as long as you can see the drone.
Exactly. If you can see it with your eyes or with binoculars, you can get power to it. We've so far demonstrated out to distances of 1 kilometer. We're looking to get out into the 2 to 3 kilometer range for some of the smaller Class 2 drones. There's also very strong interest in stratospheric drones and balloons. And so now you're talking altitudes of 60, 70,000 feet, which is 20 or plus kilometers. And so in other work, we've been studying what it would be like to do power beaming on the moon. And without the atmosphere to make tracking harder, all the turbulence in the air.
All the annoying things that atmosphere does.
Right. They go away, and so you can go much longer distances. So we're looking at tens of kilometers.
So if I was thinking about, charging my cell phone, how long would it take me to charge my cell phone?
Frequently, we're limited by the rate at which the batteries can accept the charge. In fact, one of the programs that we have just wrapped up was investigating the dual use of a directed energy laser weapon to distribute power in the 99.9999% of the time that it's not, say, shooting down drones. And the way they're designed right now, frequently they don't have to run continually 24/7, so they don't have the capacity. And so we were looking at this sort of low duty cycle burst power, and so we had to find a different battery chemistry that was commercially available that could charge fast and discharge slowly.
Okay, you have more than enough power to deliver.
Right.
It's up to them how fast they can receive it. So what do you think, what would be the answer?
For a cell phone, cell phone chargers are maybe 5-10 watts. That's usually smaller power than we do most of the time. We usually start at 100 watts and up. So we can charge a phone as fast as it can be charged as if you're plugging it into the wall.
And so a small scale drone, how long would you tell people it would take to recharge something like that?
So it has to.
The answer is going to be, it depends.
Right. But we'll be powering it, so it can be flying and operating. And then as it charges, again, it depends on what the batteries are designed to accept. But usually you can charge those in, say, an hour.
Right. And curious, could you also do comms on the same beam?
Yeah, we've done a few experiments with that. One of the biggest issues in doing optical communications is pointing the transceivers at each other. We're already doing that, and so adding, say, a different wavelength to be able to add the data to that link is a straightforward exercise.
So right now, then, what are some of the big technical challenges that you'd like to address and overcome?
There are a lot of things we're working to improve. Efficiency is one that we have sort of an odd relationship with, which is people very frequently ask about efficiency. And we're not focused on doing, say, grid scale power distribution. If you are trying to keep a drone up or whatever.
Or a sensor powered.
Yeah, or sensor powered. The electricity is not your primary factor. It's even if you're not connected to the US power grid and you're out remotely, your cost might be as high as a couple dollars a kilowatt hour, for devices that only consume a few hundred watts. That's nothing in terms of the cost of the electricity. But we still do a lot of work to keep increasing that. And that's everything from components. We don't make lasers or the photovoltaic cells, but we design everything and incorporate it. So we work with those component vendors on increasing those efficiencies. And there's a lot of design factors where you could lose efficiency if you didn't design things well. Other factors, we've been doing a lot, as I mentioned, on safety. And so it's extending the range of that and making it even more robust so that it is, as safe as an extension cord. I've done some demonstrations where I will put my head between the transmitter and receiver to show that, in fact, yes, the laser does shut off,
right.
But it's not yet a certified product and something that we would sell.
But you would think that's a solvable problem, right? Every garage
Absolutely.
door, for example, has those kinds of safety systems built in.
Yeah, we have to be a lot more reliable than those. Those don't have enough force to usually do damage. And one of the things that's different about power beaming compared to, say, a high voltage power line, an electric power line, you can get a shock that can stop your heart. For lasers, it can be a blinding hazard, but it's not a fatality hazard. but we still make sure that no one can be.
And we're not talking about the kinds of lasers, tell me if I'm wrong, or high power microwaves that could burn a body, that kind of thing.
Right. I mean, the power is there, but it's much more spread out.
Right.
It's not like welding lasers, industrial lasers like that are ones we use, and so they're used for cutting, but they focus the beam very tightly. We have the beam much larger, so it's toasty, but it's not going to instantly burn anything.
Right. So PowerLight's one of the companies working in this space.
Right.
Who are some of your competitors?
So there are a number of companies who are working at much lower power levels and shorter distances, focused on IoT devices, devices across a room. There's an Israeli company called Y-Charge that does laser power beaming, and I think their big thing right now is a little electronic displays on store shelves. And so something that doesn't need very much power, but it's a hassle to keep going and changing batteries.
So someone who works at the store walks around with a laser pointer kind of thing?
No, I think they install things in ceiling fixtures.
Got it.
Right. There are a couple of companies that do microwave power beaming. Again, for IoT devices, very, very low power sensors. And they generally have ranges of a few meters and generally power that's less than 1 watt.
Right.
There have been a number of groups, in the past and currently, who are focused on doing space solar power beaming, which is to have giant multi-kilometer sized solar farms in space and then beam the power down to Earth. There are many, many steps between here before you can have structures of that scale and everything.
But in theory, you could position them in the geo orbit, position them over the right place on the Earth,
right,
and provide power that way.
Right.
And you're saying convert solar power into that.
Yes, exactly. And it's actually, you can also do that via laser power beaming. And again, the aperture sizes, the size of your transmitter and your receiver for lasers can be, 6 inches, 8 inches. The whole thing is something you can easily fit in the back of a truck. For equivalent kind of system, a microwave power beaming transmitter and receiver have to be like 10 meters, 2-story building kind of sizes. And so the same thing goes even more so for space. They need antennas that are a kilometer across or something, whereas with laser, you could do it this big. And so lower power, earlier systems can be launched much more easily with laser. But getting back to your question, there's a few companies who are trying to work on that, but it's a very long play. We're not aware of any companies in the sort of kilowatts at kilometers market area that we're focused on. Some of the big defense primes have done programs here and there, but to my knowledge, there hasn't been anyone that's really been solely focused on this kind of power levels and distances. So,
and on the university side, is there anywhere now I can do research with faculty on power beaming, or can someone get a degree in it now?
You can't get a degrry yet. We'd love to see that. Kathy Rowe, our VP of engineering, doesn't like to talk about the mechanical engineers and the electrical engineers in the company. She wants to call them all power beaming engineers. There have been some projects out of a variety of universities. There was one a few years ago, actually, from the University of Washington, right by us, of little tiny power beaming to, I think they were trying to do something on little bugs or something. Very, very tiny receivers. There's been some work out of a UCSB on power beaming for the moon. We've worked with some groups, including at University of Central Florida. Their Creole group is a very optics-focused group. And there's a few other optics groups. But there's no degree you can get yet. The photonics clusters are the closest. So in addition to Creole...
And like you were saying, it's probably some combination of materials background, electrical background, mechanical background, physics.
Yeah.
So what about on
I'm sorry, just to add on to that, we really are doing a sort of a system of systems. There's electrical engineering for the power conversion. There's optics for all the laser. There's semiconductor physics for the devices. There's mechanical engineering for all the heat management. It's sort of, we're hiring engineers, and we say almost any discipline of engineering we probably need it.
On the government side, then,
Yeah.
Who are the big players, either doing work at their laboratories or funding work? For example, who are you working with?
Right. So one of the earliest supporters that we really appreciate is a group called OECIF, which is the Operational Energy Capabilities Improvement Fund. They're under the Office of Secretary of Defense. And they had an initial call back in 2017, I believe, for power beaming. And we were part of a government team that responded to that. And that program, the acronym was PTROL, we call it Patrol. And that had multiple demonstrations, including power fiber to a submersible vehicle, but also sort of the world's first demonstration of a high power laser power beaming system that was demonstrated at NSWC Carter Rock, where we had about 100 VIPs in, and the Navy's Laser Safety Review Board had tested all of our laser safety systems and everything, and working with the site laser safety officer, we have permission to do the demonstration with all these VIPs without them having to wear laser safety goggles or other protective equipment.
Right, because this stuff isn't going to be used by your lab techs in the field.
Exactly.
You got to make it sailor proof.
Yes.
Or even marine proof.
Right. We early on in our company's existence, one young guy who had been a Marine was talking about some of the dumb things that 18-year-olds might do. And so we're like, yeah, this equipment has to be dumped off the back of a truck and used to pound in a tent stake. And we talked about for some of the high-powered microwave communication devices, they try and throw their hot dogs into it to cook them.
Can't imagine Marines doing things.
Yeah. So our VP of Business Development is also an ex-Marine. So we certainly bring that perspective in and really try to understand from the user's perspective what's going to work, what isn't.
I think was DARPA doing work in this
Yeah,
space?
So in addition to the great support from OECIF, there's been some work and support from the Office of Naval Research. And then DARPA has had a couple of programs over the years. And there's one right now that is part of what they're calling the Energy Web. And this was started by Paul Calhoun, and it's currently being run by Dr. Paul Jaffe. And that envisions a network, just like you network data, of aerial nodes that can redirect power, just like a network router, to get it to where you need. And this program, which has the acronym of POWER, envisions taking a laser on the ground and sending it up to the stratosphere, and then relaying that through, first one to a second, then to a third stratospheric vehicle, and then down back to the ground 200 kilometers away from the transmitter. And we are part of two of the teams that are in phase one of that program.
And in theory, I guess, tell me if I'm wrong, if you had a swarm of drones, a couple of them could be outfitted to be those kinds of relays.
Exactly.
Right.
Exactly. And the reason to go up to the stratosphere is that the atmosphere is so much thinner. And so they have to be drones that can fly at that kind of altitude. But yes, you have some special drones that can carry these relays, and then you can project power pretty far down range to drones to recharge them, again, sort of horizontally from the stratosphere.
So when you think about what's going to make this technology progress, you talked about some of the advancements you're trying to make. Are there other disciplines, other engineering areas that you're hoping, their advances can be then incorporated into what you're trying to do?
So there's certainly, we've benefited from a lot of the work that's been done in directed energy for decades. There's been a lot of work in there to improve the performance of lasers. We've seen, I think, coming out of that and other areas, all the huge improvements in electronics and computational devices, machine vision that we use for tracking. There has been, for the photovoltaics, there's a lot of heritage from the concentrated solar photovoltaic work that had been done before sort of standard silicon solar cells got so cheap. The thermal management problems are similar to what's seen elsewhere. So we benefit from advancements in lasers not just from DE, but also just from industry, welding and cutting lasers. And we benefit from all these different industries and what's being done for all these components.
And you can support, if these technologies take off, maybe that industrial base, that supply chain then has a different market to serve.
Exactly. And we, as part of, tangentially related to the work we've been doing for the DoD, we've been trying to sort of map out and help build up that supply chain, especially domestically. Optics is one of the things that over the last few decades has been very expensive and harder to source in the US, but that's starting to change. And so many of the components we need and use, we need them to perform in a way that's a little different from how they're used for other industries. Lasers are a fine example. Welding lasers are great, and directed energy laser weapons are great, and lasers for other things are great. And we need some parameters that are sort of in between.
Right.
It's close enough that we can use these other ones. And that's true across the optics and all these other things. So building up the supply chain to be able to do those kind of power beaming specific components is still something we've started working on, but it's still an important factor.
So I know you've done some demonstrations and had some engagements with operational users, I think CENTCOM, for example.
Right.
What's been the reaction so far?
So there's been a lot of reaction from end users, people who've been in the field who just say, oh yeah, this would be great, we'd like to have this. From people who are on the technology development and then sort of capabilities improvement side, also see the potential. And we're just about, like I said, a year or so from now, going to be getting to the point where there'll be a system that we can hand over to someone else and start getting the really important feedback about, okay, yeah, you've got the power, but what's the next level of details of, does it need to be smaller, or does it need to be lighter, and things like that.
So things like the suitability of use in the field.
Exactly.
But so I guess people do see the potential, right? This reduces your logistics burdens. It creates this enhanced range for smaller systems or even bigger systems. And so there's some positive feedback coming.
Yes. Yeah. Not having, like I said, not having to send someone out to go change batteries, for example.
So I just want to turn at the end here to some of the dual-use commercial applications. So what in your mind do you think is going to be a first place that a consumer might see power beaming used routinely, and how long will that take to happen? So
we've had a lot of interest from telecom. As you hear about 5G radios, those are about 10 times as densely placed as the previous generation. And so there's a power delivery problem for those. So even though a consumer might not immediately see the power beaming for those, they'll see it in that these radios can be connected and their cell phone bandwidth can go up faster. Because right now, those telecom companies are facing delays up to like multiple years for the power companies to have the capability to go and install all these new power drops. I mentioned some of these other companies, the microwave and the other laser ones, that are doing these devices. So like, one company has a device for if you have a smart lock on your door, it'll keep that powered so you don't have to change the battery. And then with the drones.
For something like that, would I know the difference between whether it was solar powered like a street light or?
Probably not.
Okay.
Unless you really knew what to look for. This is something that will in many ways not be obvious. I don't want to say it's literally invisible, but people may not very well notice it unless they know what to look for. Which is good in one sense. You don't want to have some weird, big, crazy thing suddenly popping up.
Right. And so what about for cars?
People have asked that for a number of years. And in my mind, yes, you could do it, but the economics of building out all that infrastructure, I think, have been a challenge.
Right.
There's a lot of work on the sort of induction and resonance chargers that can only go, say, this far, but from the ground to a car, that's all you need.
Right.
So there's a lot of work in that for wireless chargers. You pull your car over, and I think some of the early applications are for fleet vehicles. And then people are looking at putting some of these under roads and charging cars as they go by.
Right.
So it's
Why is it that
closer.
I don't see solar cells on cars?
Because sunlight is too diffuse. The sun is a great thing, but the actual intensity of the power you can get from it is very, very low. And so you just need massive area to try and collect the sunlight.
So this has been great. If people are interested in following up and learning more about power beaming, what kinds of forums should they go to? Is there a big power beaming conference? They can run into companies like yours at NDIA events,
right?
But where does your tribe get together?
Right. It's still a relatively small tribe. Just a few weeks ago, I was at a conference in Japan. So there's one that's optical wireless power transfer, part of a photonics conference there. Every year, there's the broader IEEE wireless power transfer conference that moves around the year. It was also in Japan this year. It was in San Diego last year. I think next year it's going to be in Italy. For the first time, those in the photonics industry will know SPIE's Photonics West conference in San Francisco every year. Next year, they will start having a power beaming, optical power delivery sub-conference. There are, I wouldn't say there's any kind of particular forum that I'm aware of. There's all the different company websites. And I should mention, I will shamelessly plug that for those who have a technical focus, I'm co-author on a book of power beaming that's coming out in a couple of weeks. I'm co-author with Dr. Paul Jaffe, as well as Bernie Stransler and Mitchell Szynski. And in that book, we talk about microwave and laser power beaming systems and trying to have like a common language to talk about how you design them and where they can be used and what's the history.
Yeah, we let people plug their books, and we'll put a link to that in the text box. And now I will take the opportunity to plug some NDIA events that are coming up. I want to talk about the second annual Emerging Technologies Conference, which is going to be August 7th through 9th at the Walter E. Washington, D.C. Convention Center. Visit our website for more information. There's sponsorship opportunities, exhibitor opportunities for you to present your technical work at the conference. Keynoters are lining up. We've got Deputy Secretary Hicks, Undersecretary Hsu and LaPlante, the Service Acquisition Executives, the DIU Director, and many more. Please visit the website for that. Also, please visit ETI's website, sign up for our mailing list, and register for our various webinars, events, and educational offerings, including our Tech 101 series, and maybe we'll do Power Beaming 101 at some point. If you enjoyed this podcast, please don't forget to hit the like button and subscribe to our channel to stay up to date with all of our latest content. Special thank you to Melanie Yu and Daniel Park for producing this podcast. I want to thank once again Tom Nugent for joining us from PowerLight Technology. And with that, thank you so much for tuning into Emerging Tech Horizons.